Hello, Catherine and fellow ESET students. I'd like you to imagine yourself as this young man on the left in this picture. You're just dipping your toes in a brand new industry, and you're showing up every day eager to learn new things. The thing is, life's most important lessons are often painful to learn, and he's about to experience a lot of that pain in his near future. I know that because that's me 7 years ago at the start of my career. So you can see on this particular day, I'm quite well equipped with my tap out shirt, but even my tap out shirt couldn't save me from what was to come. Now, of course, I've survived just fine, but I've learned a lot of really important lessons since then, and I'd like to share some of those with you today and in a presentation I'd like to call Electricity and How Much It Hurts Me. So firstly, who am I? I'm Nicholas Scott, first year ESET student here at BCIT. I'm a journeyman electrician with 7 years experience and obviously a regular victim of electrocution. Now, today I want to clear up some misconceptions about electrocution, show you some fun demonstrations you can try out for yourself and one that you definitely shouldn't, and maybe make you think about electricity a little differently. Now, I'll start you off with a quote from my former boss and good friend, Scott Monula. Electricity is not to be feared, it's to be respected. And I think this is a good thing to live by. But you may ask, what exactly do we need to respect? What do I need to watch out for? Now, in order to explain that, I want to introduce three statements and play a little two truths and a lie. So the first is, it's not the voltage that gets you, it's the current. Second is current takes a path of least resistance to ground. And third is AC hurts more than DC. Now, can you spot the lie? Well, the thing is, it's not really so much a lie as it is a half-truth, but it's the first statement. I really don't like it, and I'm going to try today to convince you not to like it either. Now, let's look at a basic household circuit. So, of course, we've got a 120-volt AC source, a couple wires, and a load. Now, of course, the current through the circuit is going to follow Ohm's law, the voltage over the resistance, and if the voltage increases, so will the current. Similarly, if the resistance decreases, the current will increase. So is it the voltage or the current that's going to get you? Well, indeed it is the current that will dictate the severity of an electric shock. Very low currents can be fatal, but the thing is, they don't just appear out of nowhere. And the human body has quite a bit of resistance, and it takes a lot of power to force that current through your body. So first of all, the voltage must be high enough to produce that current. And second of all, the source must have enough power and it must be capable of maintaining that voltage. So a good example of a source that's high voltage, low power is a static shock. Static shocks are very high voltage, but there's no power there and the voltage quickly dissipates. We're not hurt by it. So what about a low voltage, high power source? Let's look into that a bit. All right, so one way that we can study this is to use a car battery. Car batteries are capable of generating an immense amount of current. This one, about 670 cold cranking amps. There's a lot of current. That's about, at 12 volts, that's 8 kilowatts of power. Wow, that's a lot of power. So, but it only does so at 12 volts. So do you think it's going to be safe for me to touch these terminals? Well, I do. I've got the positive end of my ammeter here connected to the positive of the battery. I'm holding the negative in my hand. So I'm going to complete the circuit. We'll see how much amperage flows through me. Right around 110, 120 microamps of current, very small. So even though this battery is capable of generating a lot of power, a lot of current, the resistance in my body is much too high. The 12 volts is not enough to push that current through my body. So I hope that that convinces you that there is no large current without large voltage. So now let's talk a little bit about the path of least resistance. But see, the thing about the path of least resistance is sometimes it's through me. Now, what will dictate the severity of this electric shock that I'm receiving? Well, it'll be a few things. So I'd like to have a look at a basic household cable right now. So your basic household cable has 3 wires in it. This one here, the bare, is a ground wire. And then you have your 2 circuit conductors. The black is the hot. This is the one that's live or energized with 120 volts AC. The white is what we call a neutral, and it can kind of be thought of as a negative if you're more familiar with DC systems. So I can be shocked if I just touch this black wire and a ground somewhere, where whether it be the ground from the wire or maybe something in my environment that's grounded, some piece of metal that's connected to ground. Or of course, I can touch across both circuit conductors. So the severity of the shock will be dictated by a few things. The supply voltage, of course, the resistivity of my skin, and the point of contact or path to ground. So let's look a little more in depth at shocking. Okay, so do I need to be touching the ground? Well, let's test it. Right now, I've got this wire plugged into the wall, and therefore the black wire is energized with 120 volts AC. Very dangerous voltage if you don't know what you're doing. So don't try this at home. Right now, basically, I'm going to trust this wicker chair with potentially my life. So let's see what happens when I touch the wire isolated from ground. It doesn't shock me because my body isn't touching ground anywhere. So right now, I'm energized at the same potential as the wire is. Yeah, so that's a little bit sketchy, but what would have happened if I had touched the ground? Well, let's look into that a bit. All right, so let's test this theory. So let's say the base of my lovely Fender jam chair here is the ground of my AC system. I've got my ohm meter, one end connected to the base, the other end in my hand. Let's say that this is a live wire that's going to shock me if it finds a path to ground. So let's get up on the chair here. You'll notice that as I sit on the cushion, I'm not touching the base. I'm isolated and insulated from the ground, and therefore there's an open circuit between myself and the ground. I'm not getting shocked just yet. Now let's put 1 foot on the base. So now you'll see there's a continuity through me to the ground, and so there's a path that has a certain resistance. So now I'm getting shocked, but it could be a lot worse because I could have both feet on the ground right now. So with twice as much of my body touching the ground, the resistivity of the path through my body to the ground drops roughly in half. So according to Ohm's law, I'm now getting shocked twice as bad. Well, okay, I think that's pretty straightforward, but what is this skin resistivity that I've been talking about? Well, let's look at one more video regarding that. All right, so let's look at one more scenario. So let's say instead of touching the ground with a live wire, let's say I happen to be unfortunate enough to touch both wires from a live circuit across both hands. So right now the current would be going through basically my whole upper body, and through that path I've got about 60 k ohms of resistance. So now what happens when maybe I cut my hands, maybe it's been a long day and I'm sweaty, but my hands are a little bit moist. So you can see, oh, now we're down at about 25 and counting, around half again of the resistance. So in this case, again, I'm getting shocked twice as bad. So the resistivity of your skin and the conditions of your skin can be a huge factor as well. All right, well, that all seems pretty straightforward, but you may be saying to yourself right now, well, hold up a minute, something doesn't add up here. 60 k ohms. If we put that in Ohm's law with 120 volts, it's only 2 milliamps. That really shouldn't hurt all that bad, right? Maybe I'm just a wuss, or maybe there's something else at play here. Well, see, this brings me to my last point. I like to call it Hertz. Basically, an AC voltage will be much more dangerous than its equivalent DC voltage. That's due to the capacitive properties of the human body. So as we've learned in math class, when subject to a DC voltage, a capacitor will charge to a certain voltage and then act as an open circuit. Now, the human body, this will happen extremely fast within it. So the shock when a DC voltage is across the human body is basically dictated by the resistance of the body. Now, when we have an AC voltage instead, the capacitance of your body no longer acts like an open circuit. Now it acts like a resistance that's in parallel with your body resistance. So, as we know, when we connect another resistance in parallel, overall resistance from the circuit goes down, which of course causes a larger current flow. This isn't always true, but typically shocks from AC voltages are going to be twice as bad as equivalent DC voltage shocks. So I hope I've done enough today to convince you that this statement is just, as much as it is true, it's just ugly and I don't like it. And I hope you don't like it either. To me, it looks a lot like something like this. Now, I say we fix it a bit. So we know that the current that flows through your body is going to be dependent of the supply voltage, the power of the supply, and the path that it takes. So I like this statement a lot more. It may be a little bit less concise, but it's at least right. Thank you for listening to my presentation and have a wonderful day.